So I think we're going to go ahead and move on so that we can get to maybe some dinner and a drink later, sooner. So Peter Vadas, which I realize I've been saying in my head incorrectly, just like when I learned anions and cations, I said anions and cations. So I always read things incorrectly. So now we're going to hear more on the modeling side, especially related to field phosphorus. So I'm sure everyone in this room knows Peter and all the work he's done. So I'm excited to hear you kind of summarize your whole life's work.
Right. Good. Thanks very much. Yeah, so as I said, what I'm going to talk about today is really everything we've kind of heard from, a lot about what Chad and what he talked about. How does that sort of information go into the model, and then how does that end up, once you look at phosphorus loss out of the model, how does that look at like things that that Laura and Kevin are talking about? So since a lot of this goes back to very early, right? This model that was set up for creams and EPIC. So, if you're working these things and you're wondering about this, here's just 4 papers to read, but really understand the origin of these things and what it goes back to, and some of the science and chemistry there is really helpful. So generally, this is what the phosphorus in the models like SWOT, APEX, EPIC, creams, gleams, there's other of them that are out there. A lot of them use the same approach. So basically what you have is 3 inorganic pools, and then you have organic phosphorus too. So today I'm going to talk mostly about the inorganic pools. So basically what you have is you have a labile inorganic phosphorus pool. So that is what is feeding the crop uptake, like Chad talked about, your dissolved phosphorus loss and runoff, any dissolved P that's leaching, like Kevin was talking about, that's the pool that's going to feed those pathways. And then there's the active and stable, so that's going to represent phosphorus. So I'll just say the labile is supposed to represent phosphorus. As Chad said, we don't measure what's in solution, we measure what's on the soil, so that's going to represent what's in solution and absorbed onto the soil that may come off pretty easily during a growing season. The active and stable represents phosphorus that's more tightly absorbed onto the soil, but will, as you're pulling labile out, can become labile through time. So when we look at this and when I approach this and how do we make sure that all this stuff is working well and it's a good representation, we want to make sure that the pool sizes are simulated well so we can feed our pathways. So I talked about the dissolved pathways, and then there's also this total. So if you add all these up, that's the total amount of phosphorus that's in the soil, and that's what is going to feed your sediment loss with erosion. So we want to make sure those are all the right sizes so we can feed our pathways properly, and we want to make sure, so that is, we set the model up so they're the right size to begin with, and then as things change through time, that we're able to simulate these changes in these pool sizes. So first I want to talk about just initialization. You set up the model. How do we make sure that these pools are set up the right size when we start? So there's things that we need to tell the models. It's usually how much labile P is there, this PSP, which the model uses to determine how big that active pool is, and then our organic matter that's in the soil that's going to be used to initialize the sizes of those organic pools. So those are really the 3 things that you need to be able to tell the model. So that we want to, we're estimating these, and we can check to see when the model does these things. So it's going to initialize how big the active P is based on our PSP, and then the stable P is 4 times that size. If we add all those up, does that equal what we're measuring as total P? So I'm going to get into the details of some of these things. So the first thing is initializing that labile P. So if you go back into Andrew's original papers, they measured this with anion exchange membranes. as I remember. So those membranes are designed to, you take soil, you put it in a tube, you shake the tube, the phosphorus is coming off of the soil into the water, and that membrane is like a plant root. It's taking up that phosphorus, pulling it out of solution so that more can come off the soil. So that's the experimental design. So you're trying to get at, what's in the solution plus what's going to come off the soil easily. And then what you do is that's not the soil tests that we run, the Mehlich 3, the Mehlich 1. We correlate that to our soil tests so that we can say, if we want to say labile P is that anion exchange, well, I correlate that to soil test P, and I can use my soil test P number to initialize my labile P in the model. So Andrew did all that, and so the original relationships they came up with are somewhat different. So it's the same concept, but the correlations are a little bit different. That may have been due to a function of the soils they used and the phosphorus concentration at the time that was in there. So right now, when I talk about initializing labile P in these models, I initialize it as half of Bray 1 and Mehlich 3. And equal to Olson and Mehlich 1. And as Chad talked about, sometimes, if your soil tests are not really representing that phosphorus chemistry very well, high pH soils or calcareous soils in the West, some of these relationships can start to fall apart. So if we have labile P initialized, we also need to tell the model what's that PSP, the phosphorus sorption parameters, is what it's called. So that was originally experimentally measured for the original model and the original data sets. So what that is you would take a soil, measure labile P in it. You would add phosphorus to that soil, incubate it for 6 months, and then remeasure the labile P. So the PSP would represent the percent of the added P that remained labile after 6 months. So like in SWOT, for instance, I think the default is 0.4. So 40% of any phosphorus that I add to my soil is going to remain labile, sort of at long-term equilibrium. 60% is going to go to that active and stable pools. So there again, since you're not going to be measuring, doing a 6 months incubation for every soil, we correlate these measured PSPs to commonly measured soil parameters. And so we can go to our databases and say, I know clay and organic matter, my soil test P. Here's the relationship to estimate PSP, and then that's how we would initialize the model for that. So some of the things I talked about, I'll get into some of the issues with the PSP initialization. So that's one of the things in this paper here, what we wanted to look at was, does this process, estimate labile P from soil test P, use soil parameters to estimate PSP, and if you initialize the pools and add them up, does that correlate well with total P that we measure in the soil? So that's what we did in this paper. So it's really kind of testing the SWOT approach for initializing these phosphorus pools in total P. So what we found is that that process, if you take just the original equations that were in the literature, and so I'll just go back. So we're estimating labile P as half of Mehlich 3 or Bray, equal to Olson or Mehlich 1. We'd run it through, and so we're finding that our estimated total P was less than what we're measuring when you set the model up. So I think in a slide or two I'll talk about why. So this was, you have to be careful too with some of the older versions of SWOT. They call it solution P. They didn't include that in the sum of their pools, so that would drive that slope lower. And some of the original equations, if you're underestimating your labile P from your soil test P, that may drive that even lower too. So while it's important that you can get estimates from the literature on how to initialize labile P or PSP, when you set it up and maybe you want to look at, okay, does that total that the model is saying, does that correlate well with any measurements that I have? So it's important while we're measuring soil test P, it's great to have those numbers on total P in the soil too. That really helps in that model initialization. So that's something that's important to measure out in the field. So what we did is since we're underestimating this, what we said, what if we didn't just experimentally measure PSP? What if we, estimated labile P and then calculate what PSP would need to be to exactly predict what we measured in soil test P, or sorry, total P, which is what we did. And so so basically we're calculating what PSP should be, and we relate that to our soil properties again. So we're using our soil test P and these relationships that we estimate from a calculated PSP, and then compare our measured and estimated total P. And so we can get better predictions of total P that's in the soil. So one of the things that, when I do these things, I like to find as much data as I can in the literature and throw lots of numbers at it and see how robust it is across lots of different situations, lots of different soil types. So you can see, there's a big N here. So some of the implications what we're seeing is that with our new approach, with our calculated PSPs, they were lower than what the original equations were estimating for PSP. So if you have lower PSP, that's just going to bump up your active and your stable P and your total P. So be careful with the SWOT default of 0.4. I find that that's too high for a lot of our eastern soils, sort of highly weathered soils. So if you have too little total P, then you may start to underestimate what you see. There's too little total P in the soil, so when you get erosion, there's too little phosphorus going with that eroded. So you might have to start setting parameters. Oh, I need to get my eroded phosphorus correct, and so I need to start playing with my PSP or labile P or something. And so you start to kind of adjust other things, and maybe you're getting the right answer for the wrong reasons. So that was our process went through to initialize labile P, and in some of these too, we find that PSP needs to be dynamic in the model. I think it is now in SWOT, but it used to be sort of a constant. But we see as soil test P gets really high in the soil, that PSP needs to come up too, because that's basically saying as soil test P is getting real high, more of that phosphorus is going to stay in a labile form. And that's going to, feed more runoff P or leaching. So once we've sort of initialized things properly and we feel confident with that, we also need to look at our soil P dynamics over time. So as we're doing our simulations, we've got crop uptake, we've got fertilizer or manure phosphorus coming in, we've got phosphorus runoff loss or leaching. So as we're decreasing this, the labile P, it's feeding those pathways. The model's going to let active and stable P become labile. So we want to make sure that through time that we're simulating these changes in these pools correctly, so we can feed our pathways properly through all these different kinds of scenarios. So I'll just mention that basically what's a model like SWOT is doing as labile P, as you pull phosphorus out, it's too small relative to active P then, and so it calculates an imbalance between the two, and it moves 1/10 of that per day, and it wants to always sort of reestablish that equilibrium between these pools. And it's doing something similar between active and the stable P. So if we, testing our soil P dynamics through time, so there's two things really to look at. Is if we're equating our soil test P to labile P, we want to make sure that we're able to simulate those changes in labile P through time, and they maintain that relationship between labile P and soil test P as things change. We also want to look at, does our total P in our soil, are we simulating those changes well too? Because remember that they're feeding different pathways with whether it's total P or labile P and the dissolved and sediment-bound P loss pathways. So really it's that idea of looking at multiple ways to test your model and not just looking at dissolved P loss and runoff, but multiple, tests for reliability. So there again, I go into the literature, I look at what papers are out there that they had a site, a field, and they were, adding phosphorus at different rates through the years. Let's measure changes in total P through time in the soil, given this management. I simulate that. And, can we simulate changes in measured total P and what we're estimating with the model? So, we have some of that data here for 76 different situations. And then changes in soil test P. So this is really that change in labile P through time. So there's a lot more data out there on just changes in soil test P over time. So, nearly 700 data points here. This was a paper that just came out in JEQ, where we're using a lot of the soil test P data that's coming out of Maryland now, and some of their field sites where they have long-term drawdown, soil P drawdown data. So I think, at this point, I have real confidence in the model that, you set these pools up properly, and you have a good PSP, and we really can simulate these soil P dynamics with these different balances of P coming in and out through. So I really feel like this basic model is very robust, lots of different soil types, lots of different situations. I find that it works really well. So while it doesn't necessarily represent a lot of the, the details that Chad got into, it does a very good job. So the next thing is, as we're looking at soil P changes through time, then we want to make sure that as we're simulating this phosphorus in the soil, that it's feeding our pathways of loss properly. So there again, we have our dissolved. So I'm going to look at surface runoff now. Dissolve P in surface runoff, and that's just the labile phosphorus in the models times the amount of runoff times just an extraction coefficient. And then our sediment-bound phosphorus loss, so that's the sum of our pools times how much erosion there was times an enrichment ratio. So pretty simple relationships. So I think you had this figure in one of your slides, Laura. So, when I was a postdoc in Pennsylvania with Andrew, I set about thinking that, well, this extraction coefficient needs to vary based on soil types. A high clay soil is going to release less phosphorus than a low clay soil. So I go in and I get all this data, and I just kept finding that it's just this real consistent relationship across soil types, the relationship between soil test P and runoff dissolved P. So from a modeling perspective, that was great. It's like, you can sort of use one relationship. So if you know your soil test P, then you can have a pretty decent estimate of the runoff dissolved P. And the total P loss, so this is a combination of dissolved P and sediment-bound P. So we tested this for lots of different situations too. I think this was about 25 different studies in the literature. So we find that monitoring those, if we know a runoff and erosion, we have good estimates there. We can predict the phosphorus that's going with that based on our soil P dynamics. So, I kind of repeating here, I think, with our model initialized well, if we get a dynamic PSP in the model, I think the equations, as I said, are really robust and reliable for estimating how much phosphorus is going to be moving with our runoff or erosion. Just a couple of things that we did see through the years. Some of the older versions of SWOT, I think this is fixed, and I don't know if anybody's even running some older SWOT versions. But as I talked about before, phosphorus wanting to move 1/10 of this imbalance. So for example, in older versions, that 0.1 wasn't there when you moved phosphorus from the labile to the active. So effectively what that was doing was saying that if I add fertilizer phosphorus to my soil, it would move it all to the active pool that day, and then let it kind of gradually feed back. So, and since the active pool doesn't feed anything as far as dissolved P, your phosphorus that was immediately applied would not show up in runoff at all in runoff events closely following your application. So any of that incidental loss was not simulated at all, and you could not simulate that timing at all. So, I mean, I think that's all been fixed in here. So this 0.1, kind of moving 1/10 of that imbalance for the day, we find that works really well. We've got a paper here that looked at you can make that 0.1 a little more dynamic based on how many days after application it's been, and you can get some improvements in soil P dynamic simulations, but nothing really that's earth-shattering enough to want to not use the 0.1. I think I'll skip this. This is just kind of summarizing what we've already talked about. Let me just see if there's anything. So I think just this last bullet point here is important. It's really looking at multiple things. So is my labile P, I'm looking at that, are those changes in my model being realistically simulated? Are my total P changes in the model soil total P being realistically simulated through time? And are they feeding runoff dissolved P and my sediment bound P reasonably? And is all four of those things sort of lining up? And when you feel confident with that, then I think you really have a robust simulation then. So you're not just looking at the labile P changes or the runoff P, you're looking at multiple things. So the last thing, and I'm not going to get into this at all, but I did mention that incidental losses. So I'm not, we've developed models to look at those incidental losses of phosphorus if you recently have applied fertilizer or manure. And we have, a whole series of papers on that, the development and evaluation of that. So if there's questions or things about that, I've just looked at that soil dynamics because that's sort of one of the big things we were focusing on today, but we can talk about simulating these things too. And this stuff is Amy Collick's fairly recent paper, getting this surface manure pools into SWAT. Before, the model just was not sensitive at all to incidental losses. It is now, but it's not doing it. The routines for fertilizer are not in there. So if you're looking at this timing of fertilizer issues, I have a standalone version of these routines that we could run sort of field scale to look at that timing of fertilizer application and incidental losses. And that's important here, but maybe not in a lot of other places. So any questions you have, I'd be happy to talk about.